Okay, Assalamualaikum and good morning, everyone.
Waalaikumsalam, Doktor.
Salam, Doktor. Selamat pagi.
Okay, so today we are moving to new chapter. So we have finished chapter 3 last week regarding the time response analysis. Okay, for first order and second order system. And now, starting from this lecture onwards, we are going to look at how to analyze a system stability. Okay, so from now onwards, there will be a lot of um, the terms used, okay, regarding the stability of a system. Okay, so so before we can analyze the system stability, we are going to look at a method for analyzing the stability of a system. So the method is called the Hurwitz criteria. So after completing this lecture, you will be able to determine the system stability using Hurwitz criteria for normal cases and for special cases. Okay, so for today, we are going to look at system stability using Hurwitz criteria only for normal cases. And for special cases, we are going to look at this on Wednesday. Okay, so before we go into learning what is Hurwitz criteria, let's understand what is system stability. Okay, so last week we have seen that a system response can have a natural response and also transient response. Okay, so for a natural response, a system is stable if the natural response approaches zero as the time approaches infinity. So if you look at the first figure here, this system, this example time response here, the plot or the graph, it increased at first, and then as the time increase and approaches infinity, the response approaches zero. Okay, and for an unstable system, the time response approaches infinity as the time approaches infinity. So figure 2 here, the middle figure, explain or illustrate how an unstable system behave. Okay, so if you look at this figure, the time response increases, okay, or becomes infinity when the time approaches infinity. And lastly, a system is marginally stable if the natural response neither decays nor grows but remains constant or oscillates. Okay, so the third figure here shows an example of a marginally stable system. So if you can see in the third figure, the system oscillates and doesn't show any sign of decay or grow as the time approaches infinity. So ideally, we want the system to behave following the first figure. We want a system to behave to be stable, okay? And we don't want the system to be unstable. But if a system is marginally stable, it's still acceptable. But for a marginally stable system, it can either becomes stable or unstable whenever we do some adjustment or small adjustment on the system. So dia macam tak berapa tak berapa bagus lah, dia macam atas pagar. Okay. Okay, so let's look at an example of a stable system. So let's say you are given this block diagram with this forward transfer function 3 divided by s times s plus 1 times s plus 2 and has a feedback. Okay, so feedback here has no transfer function, so the value equals 1. Okay, so when the time approaches infinity, the natural response approaches 0. So firstly, before we can determine whether the system is stable or not, we can determine the poles from the transfer function here. So from this forward transfer function, there are 3 poles, which is um, or you can simplify the block diagram first. After you simplify the block diagram, then you can find the poles from the block diagram. Okay, so the poles, then you can plot on S-plane. So the poles that are plotted here are the poles of the transfer function after you simplify this block diagram. Okay, so when we plot the poles and then we plot the time response, maybe using MATLAB, for example, we can see that the time response approaches some value, even though the time approaches infinity, or there becomes or the time response become steady. Okay? So as the time approaches infinity, the natural response approaches 0. Okay, so we know that this time response here consists of natural response and also transient response. So here, the time response approaches value 1. Okay, so the system here is stable. So this system is stable because it depends on these poles here that are plotted on the S-plane. So if you look at the poles plotted here, all of the poles are located on left half plane of this S-plane, or all of the poles are negative in values. So a stable system have poles that are located in left half plane. So when you have poles located on left half plane, then the system is stable. Let's look at an example of unstable system. So let's say you have this transfer function, and then you simplify the block diagram and you plot the poles on S-plane. Okay, and then you plot the time response. So if you look at this time response, it increases to infinity as the time approaches infinity. So the time approaches infinity, then the natural response also approaches infinity. So in this case, the system is unstable. If you look at the poles here, there is one pole on left half plane, but there are poles also located on right half plane or positive values. So the system is unstable if at least one of the pole is located in the right half plane. So when you have one of your poles that are located on right half plane, then the system will become unstable. So for a stable system, all of the poles must be located on left half plane. So if you have only one or at least one pole located on right half plane, then the system becomes unstable. Okay, now let's summarize how to determine the system stability from poles. Okay, so if we have all of the poles located on left half plane, then the system is stable. But if you have at least one of the pole located on right half plane, then the system becomes unstable. But if you have poles located on the j omega axis, then the system is marginally stable. So always remember this thing. So if you have poles on left half plane, then system is stable. If at least one pole on right half plane, the system becomes unstable. And if you have pole on the j omega axis, the system is marginally stable. Okay, so that's basically about how to determine stability from poles location. Okay, So from the poles location, we can determine the system stability. And from here as well, we can develop, or a method has been developed in order to determine how many poles, okay, that are on left half plane, or on the right half plane, or on the imaginary axis. And this method is called Hurwitz stability criteria. Okay, so again, it is a method to determine the number of closed loop system poles that are located in the left half plane or right half plane and on the imaginary axis. Okay, so to determine this, there are two steps, okay, that we can use in order to determine how many poles on left or right or in the imaginary axis. First step is to generate a Routh table, and then we can interpret the Routh table to determine the number of poles. Okay, so let's look at an example. So let's say you are given this transfer function that relates C with R, output with input. So you have this transfer function, and S divided by A4 S power 4 plus A3 times S power 3 plus A2 times S squared plus A1 times S plus A naught. Okay. So firstly, we need to generate the table. Okay. So to generate the table, what you need to do is you need to look at the highest power of S on the denominator. Okay, so here the highest power is S power of 4. So you start your table with S power of 4, followed by S power of 3, S power of 2, S power of 1, S power of 0. Okay. So always look at the denominator and look at the highest power of S. Then you need to fill the two top rows alternatingly with coefficients of the denominator. So you start with A4, you fill the first column and first row with A4, A3 uh, below A4, and then A2, A1, A0. And because you don't have any more coefficient, you put 0 for the remaining empty rows and columns. Okay, so fill the two top rows. Okay, only fill the two top rows. After you fill the two top rows, then you need to determine the next rows. Okay, like S2, S1, and S0. So to determine the value on S2, you need to use this formula. Okay, so the formula is negative determinant of A4, A3, A2, A1 divided by A3. And then the second column is negative determinant of A4, A3, A0, 0 divided by A3. And then on the third column, it's the determinant of A4, A3, 0, 0 divided by A3. Okay. So how to remember this? So so my way to remember this is by looking at the two rows above. Okay, so for S2, for example, S power of 2, it's a negative of determinant A4, A3, and then on the next column, A2, A1 divided by A3. And then on the second column, it's negative A4, A3, and then the column next to it, okay? Not the column above it, okay? Or the rows above it, okay? So it's A0 and 0. And then on the third column, it's negative determinant A4, A3, and the next column. So here in the next column, there is nothing here. So because there's nothing, you can assume there is a value 0 on that column. Okay, so that's why here it's 0, 0 divided by A3. Okay, so maybe you need more practice later. Maybe when you do tutorial, you will understand how to perform this calculation of Hurwitz table. And then for the next rows like S1, follow the same principle for S2. You need to look at the two top rows. So here you start with A3, B1, A1, B2. And then for the second column, A3, B1, 0, 0. And on the last column, it's A3, B1, 0, and 0. Okay. And similarly for row S0 and so on. Okay, so that's basically how to completely fill the Routh table. Okay, so fill the next rows by calculating the determinants. Okay, so always remember this is determinants. Okay, so later maybe when you do tutorial, you can try by yourself how to calculate this. Okay, so after we generate the Routh table, then we can interpret the table. So to interpret the table, what we need to do is we need to look at the first column of the table. So the number of roots of the polynomial or the number of roots of the denominator that are in the right half plane is equals to the number of sign changes in the first column. If there are sign changes in the first column, then the system is unstable. Okay, so let's look at an example. What is this interpretation says? Okay, so let's say you have this block diagram with a forward transfer function 1000 divided by s plus 2 times s plus 3 times s plus 5, and it's a unity feedback. So firstly, we need to simplify the block diagram. Okay, so this is a feedback loop. So you use the formula for feedback to simplify the block diagram. Okay, use feedback formula. So you get this transfer function after you simplify the block diagram. Okay, so firstly, always simplify the block diagram. And then further expand the polynomial to get in this form, okay? You don't want the denominator in the factorized form. You want it in a complete multiplied form, okay? Then after that, we generate the Routh table. Okay, so this is the denominator. So we take the denominator and look at the highest power of S. Okay, so the highest power is power of 3. Then we can generate the table starting from S power of 3, followed by S power of 2, S power of 1, and S power of 0. And then we fill the two top rows. Okay, we fill the two top rows here with the coefficient of the denominator. So here the coefficient equals 1. So you put 1 here. And then this is 10. So we put 10, 31, 1030. And then you put 0 here. Just you can put or you can just leave it. Okay. So here in this example, the example just put 0. Okay. So after you completely fill the two top rows, for the row S2 here, you can simplify if you want. Okay. So here, what the example did was, because this is 10 and then this is 1030. So you can factorize 10. Okay. You can factorize the value 10 to make the table more simplified. Okay. So when you factorize value 10, then the second row becomes 1. And then 10,030, you factorize 10, then you get 103. But you can choose not to simplify. Okay. The answer will be the same. Okay. So tak kisah nak simplify ke tak simplify, the answer will be the same. And then after you fill the two top rows, then you can start filling the next row, row S1. So this is done by calculating the determinant. So how to determine the values here? So it's a negative determinant of the value 1, 1, 31 and 103 divided by the row above. Okay. And then similar to the second column, so it's a determinant of negative determinant of 1, 1, 0, and 0 divided by the value of the row above. Okay. And then lastly, for the third column, it's a negative determinant of 1, 1, and then 0 here. Okay. Divided by this value 1 here. And then similarly for row S0, you can find the first column by taking the negative determinant of 1, negative 72, 103, and 0 divided by the value of the row above. Okay, and similarly for the other columns. Okay. So later maybe you can try by yourself on how to generate the route table. So here we have generated the route table from the example. Then we can interpret the table. Okay, so to interpret the table, we need to look at the first column. Okay, so look at the first column and then calculate how many sign changes. Okay, how many sign changes in the first column. Okay, so here in the first row, row S3, the sign is positive. Okay, the value here is positive. And then row S2, the value also positive. And then the value on row S1, here it's a negative value. And then the value of row S0, it's a positive. Okay. And then you calculate how many sign is changes from row to row. Okay. So from row S3 to S2, no sign changes because from positive to positive. And then from row S2 to row S1, there's a sign change here, positive to negative. So yes, one sign change. And then from row S1 to S0, you have another sign change here from negative to positive. So there are two sign changes here that you can calculate, okay, that you can determine. So because there are two sign changes in the first column, so meaning that you have two poles on the right hand side of the S-plane, and because you have positive poles or poles on the right hand side, then the system is unstable. Okay. Any question before we move on to another example?
Doktor, kalau tak ada changes, Doktor?
Kalau tak ada changes, maksudnya sistem tu stable. Dia tak ada poles on right hand side. Semua poles dia dekat left hand side.
Maksudnya kena
Maksudnya a stable system, sistem yang stable, dia punya poles, dia punya Routh criteria ni dalam first column tu semua positif, tak ada negatif. Maksudnya sistem tu stable.
kena describe Doktor selepas table ni. Ke
Selalunya soalan akan tanyalah, dia akan tanya determine the system stability by using Routh criteria, for example. Dan kena ceritalah berapa banyak sign changes, berapa banyak poles on right hand side ke left hand side, and then baru boleh tahu sistem tu stable ke tak stable.
two pole of
Okay.
right hand side of S-plane tu yang mana, Doktor? Two pole on right hand side.
Okay, so dalam denominator ni kita ada power 3, s power of 3. So kalau polinomial tu s power of 3, maksudnya dia ada 3 poles lah. Okay. So sistem ni ada 3 poles. So we can determine the poles using calculator. Okay, kita boleh guna calculator untuk cari poles dia. But sometimes when you have denominator yang sangat banyak, contohnya s power of 9 ke, for example, s power of 9. So ada 9 poles. So bila ada 9 poles, nak guna calculator tak boleh dah. Okay, so calculator kita, kalau saya punya ni Casio FX 570, boleh guna sampai power of 3 je. Okay, so kita tak boleh nak cari poles. So dalam case ni kita tahu ada 3 poles. So bila ada 3 poles, kita buat Hurwitz criteria ni, kita generate the table and so on. Then from here, we know that there are 2 sign changes. So maksudnya ada 2 poles yang located kat sini. Okay. Tak tahulah kat mana, tak tahu kat mana dia located, tapi dia left hand side, right hand side, sorry. Ini 0, J omega. J omega. So maksudnya ada 2 poles yang positif, ada 1 poles yang negatif, maybe sini, tak tahu kat mana. So tujuan Hurwitz criteria ni, kita tak payah tahu poles tu berapa value dia, tapi kita boleh tahu dia positif ke dia negatif. Macam itulah konsep dia.
Okey, Doktor.
Okay. Tak apa, nanti try buat tutorial kot. Lepas raya. Okay, any more question before we look at another example? Okay, so please understand this Hurwitz criteria, because in later topics, this Hurwitz criteria method we will use a lot. Okay, and sometimes maybe dah week 10 ke, for example, saya assume korang semua tahu apa benda Hurwitz criteria. So maybe saya just laju-laju je kat situ. Okay, so please understand this method, and later on bila ada masa lepas raya ke, try to look at the example and also look at the tutorial given to you. Okay.
Okay, Doktor.
Okay, so let's look at an example of how this Hurwitz criteria is actually applied. Okay, applied for determine some other things in automatic control. So for example, here you have this transfer function Ts equals k divided by s cubed plus 18s squared plus 77s plus k. So sometimes you are given this value of k, and this value of k is called the gain. So in automatic control, you have the term gain. So this value k here is the gain, and when you change the value of k, the system stability is also changes. Okay, so later on, maybe in next lecture, we will see more about this gain. Okay, so one of the things that you need to adjust in your system is by adjusting the value of k here. So when you adjust k, the system will change, the stability of the system will change. So how to determine a suitable value of k to make the system is working in a stable condition. So this is we are going to look at how to determine this value of k. Then from this transfer function, we can generate the Hurwitz table. Okay, so as usual, you start with s power of 3, followed by s power of 2, and so on. And then you fill the 2 top rows. So 1, 18, 77, and k. And then you calculate row S1 using the determinant. And then you calculate the second column also using the determinant. And then you calculate the row S0 or S power of 0 also using the concept of determinant. Okay, so when you fill the table completely, then you can start interpreting the table. So by looking on the first column, so we look at the first column. So if we want the system to be to work in a stable range or to be stable, then we must make sure that the first column here, the value on the first column must be positive or has no sign changes. Okay, so here row S3 is already positive, similar to row S2. And then on row S1, we have K here. So we don't know the value of K. And we want this to be positive, okay, bigger than 0. And similar to row number 4 or row S0, we want K to be positive as well. So from here, we can determine the range of K or the suitable value of K for this column to have all positive value. So we look at the first row here, I mean the row S1. So 1386 minus K divided by 18 must be positive. So we get K must be less than 1386. And similarly for row S0, K must be positive. Okay. So we can combine these two range. So then the range for K to make sure that the system is stable is in between 0 and 1386. Okay, so when you tune the value of K, you must make sure that the K cannot be negative or cannot exceed this 1386. Must be within these two values. Okay, so that's how you use Routh criteria to find the range of K or the range of the gain for a stable system. Okay, any question before we end this lecture?
Doktor,
Hmm?
cuba doktor tengok example 1 yang tadi tu, yang root Hurwitz table. Untuk S1 tu, yang row nombor 3 tu kan, macam mana dapat tu doktor? Negative 1
Ni.
metric 0 ada kan?
Ni Okay, so dia negative 1, 1. And then you tengok kolom sebelah dia pula. So kolom sebelah dia tak ada apa-apa. Empty. 0, 0.
Oh,
Okay?
ambil kat situ.
Sama macam kolom yang ni juga, yang tengah ni.
Ambil quality
1 dengan kolom sebelah dia. Betul. So kolom yang ketiga ni pun sama. 1 dengan kolom sebelah dia. So kolom sebelah dia tak ada apa-apa, empty. So just 0, 0 lah.
Okay, faham. Okay, doktor. Sorry,
Okay.
doktor.
Tak apa, okay je. Okay, any more question? Before we go to the class on Wednesday, please try to understand the concept that we have just learned today. And on Wednesday, we are going to look at how to apply Routh criteria for special cases. Okay. So I hope you understand the concept. Maybe tak berapa nak dapat lagi hari ni, but you can try follow the exercise later in your lecture notes. Then on Wednesday, we look at special cases, and maybe after Raya, we will discuss the tutorial. Okay, so regarding your quiz number 3, it's already uploaded in Kalam, and please do it. And the due date is on Friday. Okay, And I think that's it for. Oh yes, your project part 2. The due date is on Wednesday. Okay, Wednesday pukul 11:59 malam. I think that's it for today. If you have any question, you can ask me through WhatsApp. Okay, so that's it for today. Thank you very much. Assalamualaikum and goodbye.
Thank you, Doctor.
Thank you.
Good, Doctor.